Now, if we discuss the syllabus of inorganic chemistry, here in inorganic chemistry, we have 5 units. And out of the 5 units, the first one is coordination chemistry, main group, organometallics, lanthanides and actinides, and bioinorganic chemistry. So basically, the major part of the inorganic chemistry syllabus lies in OMC plus coordination chemistry. So if you're planning to do inorganic chemistry, first thing I will suggest you to do these both of the chapters full units completely. This almost constitute approximately about 60% of the total inorganic chemistry syllabus. They approximately constitute 60% of the entire syllabus. After which you can focus on the topics like main group and lanthanides, actinides, and bioinorganic. Now, the thing is in bioinorganic, the part is all about memory. And the similar thing is in main group and lanthanides and actinides also, it's about memory. Nowadays, the questions have increased from lanthanides and actinides in NET. If you see nowadays in CSIR NET, the questions have increased from lanthanides and actinides. So you can't leave this topic and consider it to be like not of any use. This topic is very important nowadays because the questions have increased. Further, the thing is the most questions asked from them is from spectra or magnetic property. Now we will be discussing about the syllabus of coordination chemistry, in which you have structure and isomerism. Basically, structure corresponds to your ligands. You should know about all the ligands here, which are like denticity of ligands, which is monodentate, tridentate. That is the donor ability of a ligand. Moreover, isomerism talks about the geometrical isomerism, in which you have optical active and optically inactive molecules. This you have to study in square planar, tetrahedral, and octahedral. You should know about the entire concept of this. You also have isomerism like hydration isomerism, and coordination isomerism. You can study those also, but you can expect more questions from geometrical isomerism. Moving further, you have VBT, in which you calculate the hybridization. In hybridization, you can find the geometry of the complex after calculating the hybridization. And you have Huggins complex here of copper. Huggins complex, that is an exception. You can see it. Moreover, you have here inner orbital complexes and outer orbital complexes in octahedral. And if you talk about, you can also see a hybridization of HD3 in tetrahedral. That also you should remember. And you should also know the difference between square planar and tetrahedral. So these are the primary things you should know in VBT. Moving further, you can also study, when you study CFT, you will see that there are different energy level diagrams based on various geometries. Like if you have square planar, square pyramidal, or you have tetrahedral, octahedral, or you can also have square antiprismatic, trigonal prismatic. So these are the some geometries. You should focus on trigonal pyramidal, bipyramidal. Focus on these geometries, and you have to remember how you can find the different energy level breakup of different orbitals, d orbital split basically. You should know how to calculate CFSE energies, that is the basically stabilization energy, and the application of CFT are in hydration energy and lattice energy. So you should study this, as many questions are being asked from this. Last is the John-Taylor distortion, which GATE generally asks many questions because it is a very important and a basic thing. John-Taylor distortion, you should know the principle and what is the basically split of orbitals during John-Taylor distortion. There are how many types of John-Taylor distortions? Compressibility and elongation. So basically, these are the basic things. The questions are asked like which is John-Taylor active, which will give distortion, which will not get distortion. Moving further, we have MOT based on ligand field theory. Here you have term symbols and the names of orbitals like P is T1U, and D orbital, if it is DZ square or DXY, it can be T2G. So these are different naming of orbitals. You should remember. From this only you can tell about the pi donor ligand or pi acceptor ligand, or also about the sigma donor. This all comes from your MOT. Moving further, you have electronic transitions of metal complexes. Here, there are basically selection rules like Laporte selection and spin selection. These are the very important parts, Laporte and spin selection. You should remember what is Laporte selection rule basically, and it is against the symmetry transition. Okay, it is against the symmetric transition. Further, you have Russell-Saunders coupling or LS coupling, that is orbital and spin momentum gets coupled together. Last is how to find the term symbols for a complex as well as for a free metal, because the term symbols are different. You should know how to calculate the term symbols. Then there are spectral details. And as you study about spectral details, it tells about the number of transitions and what are the transitions possible in the complexes. Number of transition and what is the transition? And is the transition allowed or not? These all are the questions which you can expect during transition spectral details. Moving further, here there is a contribution of JTD also when you get a broadening. So in spectra, you can get a broadening, which is due to JTD. Further, there are some exceptions which are against the selection rules. Basically, if some transitions are not following the selection rules, but we still have the transitions. So these are based on vibronic coupling, And there is a spin selection rule, which is not valid like in case of Mn complexes. So in Mn complexes, spin selection rule is not valid. So basic, these are the things till yours electronic spectra. Moving further, you have Orgel and Tanabe-Sugano. You should know about the basics, like what is the plots, what are you plotting on X and Y, and you should know about what is the difference. Orgel is for high spin, Tanabe-Sugano is for low spin as well. Plus, here the ground state energy is not zero. Ground state energy is not zero, whereas in Tanabe-Sugano, the ground state orbital energy is taken to be zero. And in Orgel, we don't use any contribution of nephrostatic effect or Raka parameter. But basically, here in Tanabe-Sugano, we are plotting with Raka parameter. So Raka parameter beta is important here. Moving to nephrostatic effect, it tells us about the covalent character in a complex. And Raka parameter is the opposite of nephrostatic effect. So basically, you should know the orders. You might be asked about the orders of nephrostatic effect and Raka parameter. So you should know about the orders. And there is also a transition formulas. Like, so moving further, you have magnetic properties. Magnetic properties, you have spin and orbital contribution, in the entire magnetic moment. So basically, if we talk about, there is a concept of quenching and calculation of mu effective, in which you get the formula of 1 minus alpha lambda by delta, where you have alpha values as 0, 2, or 4. You have to put the values directly and you will get the answer. So basically, these are the basic things in this. Plus, you should also know about the orbital contribution. You should also know about the orbital contribution in magnetic properties. Like T unsymmetric, give orbital contribution. Plus, you have a concept of LS coupling here. So you should focus on these topics also in the magnetic properties. So if I tell you one thing, major thing here is, if you tell you one major thing is, the most important part of the questions is JTD, applications of CFT, and energy level diagram of different geometries. Plus, you can get questions from Orkal and Tanabe-Sugano. What are the possible transitions? Majority of the questions coming from nowadays are from the possible transitions, and about the term symbols. So these are very important nowadays. These four. These four are very important if I tell you. Electronic spectra, Orgel, Tanabe-Sugano, nephrostatic effect, magnetic properties, as well as charge transfer is also important because it is highest intensity. You have DD transitions and charge transfer. Basically, charge transfer has the highest intensity. Further, magnetic properties questions are asked very regularly from nowadays. Vedat and Bela twist are added in some years ago only in GATE exam, and rarely the questions are asked from Vedat and Bela twist. You can check it once. It is in square planar complexes. Moving further, reaction mechanism. See, it's at the last. It doesn't mean that it is not of any priority. It is the most important topic of the coordination chemistry, and here you get the concept of lability and stability. Lability and stability. So basically, kinetics responds to lability and thermodynamic is responsible for stability. So basically, if moving further, you have substitution. Substitution is SN1 type reaction, which is dissociative, and SN2 type, which is associative. You should know about which complex will give SN1 and which will give SN2. Further, you should know that which are labile and which are inert. You get questions from hydrolysis also in this. So you should know about the HSAB principle is also one of the most important part here. When we're talking about lability and stability, the two important factors depending are CFSE and JTD. These are very important factors for lability and stability. Moving further, substitution, you have SN1, which is dissociative, SN2, which is associative. You should know the geometries. You get questions from hydrolysis. And further, HSAB principle, hearts of acid base concept is very important for this reaction mechanism. Last but not the least is your redox reactions. Last but not the least is your redox reactions. And if you talk about the redox reactions, they are the most important for nowadays, in which you have inner sphere mechanism and an outer sphere mechanism. Then you have Marcus theory here. Marcus theory, region of inversion. So you get questions regularly. This also comes in your photochemistry part, but you can study it in this coordination chemistry also. You should know what is the difference between inner sphere and outer sphere. You should know that how the reactions can happen and which will be the most fast. There are many things which you need to remember, but this is very important. So this is the basic syllabus discussion of your coordination chemistry part. Further, we can discuss is your topic is organometallics. First, we will discuss organometallics. So basically, if you talk about organometallics, as you know that 18 electron rule is a very basic topic, right? You must have studied during the bachelor's what is 18 electron rule, and some do not follow 18 electron rule. So exceptions also are important here. Exceptions. Moving further, one thing which is not mentioned here is reaction mechanism, which is most important, and reaction mechanism and hapticity. So you should study what is hapticity. That is also number of carbons or number of atoms basically connected in donation. Moving further, reaction mechanism which I am discussing, it is oxidative addition and reductive elimination. Then you have the last third one, which is migratory insertion. Migratory insertion. First is oxidative addition, reductive elimination, migratory insertion, and last is beta elimination. So you get many questions regarding this. And if you don't do these reaction mechanism, then it will be very difficult for you to understand the further coordination chemistry. So these reaction mechanism and exceptions of 18 electron, which are not mentioned, are also important. Moving further, we have metal alkyls. Metal alkyls, like what is the metal carbon bond strength and what is carbon carbon bond strength. Similarly, here we have carbon oxygen bond strength and metal carbon bond strength. Back bonding concept, which is very important here. Back bonding. Further, in metal olefins, you can be asked about carbon carbon bond strength. So these are also very important in metal alkyls, metal carbonyls, and metal olefins. Moving further, the interesting part of this is the carbenes, which is Fischer carbene and Strock carbene. And you get a lot of questions from Fischer and Strock carbenes. Statement questions are also asked according to their reactivity differences. So you should study them closely. Fischer and Strock carbene. Further, you can also study carbines. If you get time, you can also study carbines, which is singlet and triplet carbine. And once you are completed with the second point, third is metallocene, which is sandwich complex. And you get generally 3D sandwich complex between cyclopentadiene ring. So basically, cyclopentadiene ring, you get this complex, and questions are asked according to their MOT, and different 3D metals are substituted inside, like CP, M, CP. And this M can be any 3D metal, and they will ask you about the properties of that metal. You also have one thing which is CP star, which is more electron rich in comparison to normal cyclopentadiene ring. So this is the third point of metallocenes. And staggered and eclipsed metallocenes difference also you should know. Further is metal-metal bonding, in which you have sigma bond, pi bond, then delta bond. So how many electrons are required for delta bond? ReCl8. This is the most major questions asked from multiple delta bonding of ReCl8. These questions are regularly asked. Further, we have fluxionality. Fluxionality means different transitions of a compound based on the temperature. So basically the structure keeps on changing as you have studied in very pseudo rotation in chemical bonding. It is similar to that. Here, the question are asked from ring whizzing and bridge scrambling. Bridge scrambling. So basically the questions come from here, and they ask you about the NMR here. They will ask you about the NMR spectral difference according to temperature, relation of NMR with temperature. And you can expect regularly questions from this topic, okay? So these are the topics which are covered in fluxionality. Further, if we discuss, we have types of reaction like hydrogenation, Wilkinson catalyst, selective. It's selective. So you also have many different catalysts of hydrogenation. So most important is Wilkinson. So you can also form a carb tree catalyst. Carb tree catalyst. So that is, we increase the reactivity and decrease the selectivity of reactions. Further, you have hydroformylation, in which you form linear and branched aldehydes. So you should know that how to increase the level of linear aldehydes and decrease the amount of branch you are getting. So you can use different ligands. Here you get the concept of your bite angle and your cone angle. These are also very important, bite angle and cone angle concept. Further, you have acetic acid, in which you have Monsanto and Cativa. These are the two primary differences. You should know what is the difference between the two. Then you have olefin metathesis, in which you use different olefins and create new types of olefins from them. Basically, you regenerate olefins by reacting different olefins together. Here you have to study about Grubbs catalyst. Grubbs catalyst of first, second generation, and which is the metal you use in Grubbs catalyst. You also have Strock's catalyst. You have many different types of catalyst also. Mains are Strock's and Grubbs catalyst. You should study about them. Further, you have olefin oxidation, which can be a part of oxidative addition. Oxidative addition. So basically, this is the part. And one more part which is not mentioned here is your isolobal analogy and Wade nomenclature. So you should remember this isolobal analogy and Wade nomenclature questions are asked very regularly from, and boranes. Basically, boranes, Wade nomenclature. These questions are very regularly asked, and you should prepare them properly. This part can also be considered to be under your main group, but generally you can study it with the organometallics only. So please prepare these topics, very important, like Clozo, Nido, Arcano are asked very regularly these days. So this is the basic part. And last is the Fischer-Topaz and Ziegler-Natta. You should know that which are the reagents used in these reactions. It's not like very frequently as nowadays, but you should know what are the reagents used in them. So this is the basic syllabus discussion of your coordination chemistry and organometallics. So this is the 60% syllabus, and I've discussed the points. So you should focus on these points very properly and do with them, memorize everything, because the most important part of inorganic chemistry is memory part. if you forget. So you should practice a lot of PYQs of GATE and NET. The more you practice, the more you will learn in GATE and NET for inorganic chemistry, and you can easily increase your score. You can easily increase your score if you do good in inorganic chemistry, because physical and organic are like not fixed, which will be tough and which will be easy. But if you consider that inorganic will be medium, so this considering it to be medium, you should know that the primary thing you should do is do coordination and organometallics properly and spend a lot of time on them. Further, if you get time, you can do main group and lanthanides and actinides. First, main thing is in lanthanide and actinides, as I mentioned, that spectral magnetic properties and spectral properties are important. Now we'll be discussing the syllabus of main group chemistry. Basically, main group chemistry, the major topics are oxo acids, shapes and reactivity, and their naming. Naming of oxo acids is very important. If we talk about the naming of oxo acids, it's very important. Then from the structure and bonding of silicones, silicates, boron nitrides, alpha, beta, gamma, borazine, benzene equivalent. This is very important because it's equivalent to benzene. Then phosphazine. It is partial delocalized. You should need to study the entire property and the previous years of this. They're very important. So basically, here you need to study these 4 to 5 things are very important here, and plus oxo acids are also very important. When you talk about the allotropes, generally the questions are rarely asked from allotropes, but the main questions lie from silicones, silicates, boron nitrides, borazines, and phosphazines, plus the oxo acids. Even the questions are rarely asked from pseudo halogens and interhalogens, but yes, noble gases, the questions can be asked. And the questions asked are reactions of Xe with F to make different XeF, F2, F4, F6, and XeOF2. So these are the different molecules which are formed. So they ask the hybridization, the shapes, the reactions for these in main groups. As I mentioned, oxo acids, silicon, silicates, these are important. Rest you can look after if you get time, but the major focus should be on these topics. And last, talking about bioinorganic, I will say that you should know about hemoglobin, myoglobin. Basically, if you don't study it properly, don't worry. Hemoglobin and myoglobin. This should be the basic focus on hemoglobin, myoglobin, and your further hemocyanin and hemerythrin. The questions are regularly asked from them. Basically, hemocyanin and hemerythrin. These are the 4 very important parts of your bioinorganic, and you can expect a lot of questions. Further, if you can study your ferredoxin and rubidoxin, and nitrogen fixation. But I will suggest you do these 4 things properly and study the previous years of the others. Just try to study the previous years. You might get the same questions in your net, repetition of questions in net. So this is the basic syllabus discussion of inorganic chemistry has been done.